Alright everyone, what we're talking about today is measuring electric fields. By the end of the lesson, we will have defined what an electric field is. We're going to determine how charges affect an electric field, and then we're going to talk about the two ways where we can calculate the strength of an electric field at a particular point. Now, we've already discussed before that you can be a positively charged object, negatively charged, or you could also be neutral. Now, the two images you have in front of you, let's talk about the one on the left first. There is a positively charged object, and there are lines that come outwards from it. What these lines describe is how you would feel a force, in what direction you would feel a force if you were a positively charged object. Because we know like charges repel from each other, that's why the arrows point away. Because if you were a positively charged object, you would feel a force away. For a negative charged object, if you were a positively charged object, we're keeping the same assumption, you would feel a force towards the negatively charged object because opposites attract and you would feel attracted towards this object. Now these lines combined together describe what's called the electric field. And what it is it describes how the area around these charges will be impacted because of the presence of these charges. So an electric field is the area around a charged object. Depending on where the arrows are pointing tells you in what way a positively charged object would feel a force. Now, what we're talking about is the electric field strength. Now, how much push or pull a test charge experiences because of the electric field is what we're going to call the electric field strength. Now there are two scenarios in front of you. The one on the left is where there is one positively charged object and there are arrows pointing outwards from it. But as you can notice on the edges, as you get further and further away, the lines start to get dimmer and dimmer. What this indicates is that the strength gets less and less. The forces that you'd feel are weaker and weaker the further away you get. Now if we compare that to the image on the right where there are 5 or 6 positive charges, the arrows never dim out because they remain a lot stronger as you go outwards as compared to the first image. So the caption I've written is, notice how the arrows in the diagram on the left start to become dim as they get further from the center of the field. When compared to the diagram on the right, this means that the electric field is weaker. So what I'm trying to introduce is the word strength. So when the field is stronger, you feel a harder push or pull, and when it's weaker, you don't feel that hard of a push or a pull. Now, one of the ways to measure or to describe how strong an electric field is if you compare the strength of the push or pull, and because in physics push or pull means force, we're talking about the strength of the force. So if we compare the strength of the force with the charge of the test charge, then we'll just divide those two values and what we'll get is a value that describes the strength of the electric field. Now just to remind you, a test charge is just a small positively charged object. The only point of it is to be placed in an electric field and to observe how it reacts. So that's why we call it a test charge. It's just a small charge that you place in an electric field, you observe how it's being pushed or pulled away, and because or based on that, you can measure the strength of the electric field. Now let's talk about an example. So here it says, suppose that you're measuring an electric field using a positive test charge of 3.0 times 10 to the negative 6 coulombs. This test charge experiences a force of 0.12 newtons at an angle 15 degrees north of east. What are the magnitude and direction of the electric field strength at the location of the test charge? So let me get my pen out here. Now let's draw out what we have. We have a test charge that's experiencing a force of 0.12 newtons at an angle 15 degrees north of east, or in another way to say it, above the horizontal. Let's write out what its charge is. This charge is 3.0 times 10 to the negative 6 coulombs. And what we need to find is the magnitude and the direction of the electric field strength. So let's write out what the equation that we just wrote out before. It was E is the force that the test charge experiences over the charge of the test charge. Now you can see pretty clearly that all the given information is all we need to find out what the magnitude and direction of the electric field is. So pretty simply, the strength of the electric field is 0.12 newtons, and the charge of the test charge is 3.0 times 10 to the negative 6. Now just really quickly, I'm going to do this on my calculator. And the value that I get is 40,000. And this is going to be newtons per coulomb. All right, pretty simple. What this value means is that for every charge that your charged object has, it will feel 40,000 newtons of force. So the bigger the charged object, the more force that it will feel. Let's move on. Let me clear my screen first. All right. The slides you saw previous were just some more examples, and you'll have access to this PowerPoint presentation, so you could do those on your own. The next thing is the second way to calculate how strong an electric field is. Now what we're going to do is combine Coulombs law with the relationship that we just drew out. So what I mean is Coulombs law is Q1 Q2 over R squared. If we combine this guy with force on Q over Q, combine these two, the math will spit this out. And what this is another equation that can be used to calculate the electric field strength. K is still Coulomb's constant. Q is the charge, and not of the test charge this time, it's the charge of the charged object that is creating the electric field. And R squared is how far away are you measuring the electric field strength? How far away from this charge are you calculating the electric field strength? Now, I can break down the derivation of the equation later on, but that's not the focus of this video, so maybe we'll do that another time. But just to repeat, K is Coulomb's constant, Q is the charge of the charged object, and R is how far away are you from the charged object are you measuring the electric field strength. So to demonstrate this, let's do another example. What it says is, what is the magnitude of the electric field at a point 0.30 meters to the right of a small sphere with net charge negative 4.0 times 10 to the negative 6. All right, let's draw that out. So what we have is a charged object, and it says that it's negative 4.0 times 10 to the negative 6 coulombs. Now, just to remind you, because it's negative, I want you to imagine field lines that go inwards towards this charge, because that's what we draw for negative charges. And they want to know how strong is the field 0.3 meters to the right of this sphere that's creating a field. So what is the magnitude of the electric field right here? How strong, how hard are you going to be pulled towards, or at this location, how strong are you going to be forced towards the negative charge at this location? So to demonstrate the equation, K, Q over r squared. K is still Coulomb's constant, 9 times 10 to the power 9. Q this time is not the charge of the test charge like it was in the previous equation. Q is going to be the charge of the thing that's creating the field. So the thing that's creating the field has a charge of 4 times 10 to the negative 6. R is how far away are you measuring it. Now, of course, if you measure the strength closer, you're gonna have a lot larger force than if you're a lot further away. So your distance from the charge definitely has an impact on the strength. That's why this is in the equation in the first place. So what we're going to do is write the distance that we're measuring from it, and we're measuring it at a distance of 0.3 meters. Let's not forget to square it. Again, pull out the calculator. I get a value of 40, or no, that looks like 400,000 newtons per coulomb. All right, those are two ways. That's the second way of calculating the electric field strength. And of course, whether or not you're going to use this way or the other way depends on what information is given. So if you don't know how much force a test charge experiences, then you definitely can't use the other equation. Whereas we are able to use this equation because we are given a distance and we're also given a charge value. So writing out your given list and your given and unknown list is super crucial when it comes to solving problems like this. All right, there's a solution. Here's some more practice problems and some answers. And to summarize, the electric field is an area around a charged object that describes the direction and magnitude of the electrostatic force. So to put it simply, it is a picture that shows in what direction you're going to be pushed or pulled because of the electrostatic force. The strength of an electric field can be determined in two ways. You can either compare the electrostatic force F to, so the electrostatic force is what we wrote down as F on Q, and comparing it to the charge of the test charge, which we wrote as Q prime. That's the first equation. And the second way is by relating the charge of the charged object with the distance from it, which gave us this equation. So just putting them side by side. These are the two equations for solving for the electric field strength around a charged object. If you have any questions, throw them at me. Thanks for watching, and I'll see you next time.